All right, guys, so we are going to look at the quantum mechanical model, which is our current model of the atom. This kind of is based off of Bohr's model with the electron cloud model. So not necessarily that the electrons are in orbits, but they have certain areas around the nucleus that they can be. So this model determines the allowed energies an electron can have and how likely it is to find an electron in various locations around the nucleus. So we have zones around the nucleus where we are likely to find those electrons. And this is based off of probability, but it does not limit electrons to energy levels. So this is where they're likely to be, but they can still be elsewhere around the nucleus. This model was developed by Erwin Schrödinger. He had mathematical equations to find these zones or areas. All right. So with the quantum mechanical model, we end up with atomic orbitals. These are not the same as the orbits from Bohr's model. They're derived from those, but they are not the exact same. They're not pathways that the electrons travel. So an atomic orbital is a region of space in which there's a high probability of finding an electron. So where electrons are most likely going to be, these are three-dimensional spaces around the nucleus. And these orbitals were found using Schrödinger's mathematical equations. So by using probability and some calculus, they figured out these three-dimensional places that come in different shapes and sizes. So there are 4 different types of orbitals we come across. You do need to know these with the shapes for some of them. So we have the s orbitals, which are pictured on the left, where it is a sphere around the nucleus. So s orbitals are sphere. S orbitals are the ones with the lowest amount of energy as well. Then we come into the p orbitals. The p orbitals look like dumbbells, or some might refer to it as peanuts, where it has that small part in the nucleus and it's 2 lobes, like a figure 8, that go out from the nucleus. So they're dumbbells that they are small in the center and then balanced on each end. And these can point in different directions. They can be on any of the axes. Then we have d orbitals. Don't worry about that one at the top. It's a hybrid one. But d orbitals we refer to as cloverleafs or double dumbbells. So think of like a 4-leaf clover. It has the midpoint where all the leaves connect, and those 4 lobes that go off the side. And yet again, that can change and rotate its orientation as well. And then we have f orbitals. You do not need to know the shape of f orbitals. We rarely use f orbitals simply because these are some of those largest elements that we come across. Excuse me. These are some of the largest elements we come across, and they have varying shapes. They can have different lobes on different planes. So, excuse me. So know that the orbitals go S, P, D, F. Those are going from like lowest energy to highest energy. And you need to know the shapes of S, P, and D. So know that S is a sphere, P is that dumbbell or peanut, and then D is that cloverleaf or double dumbbell. So, like I said, these are different from Bohr's orbits, but they're derived from Bohr's orbits. So Bohr's energy levels, those orbits, in the quantum mechanical model, we refer to as principal energy levels. And these energy levels are what are split into the S, P, D, and F sublevels or orbitals. So that's kind of the background part to the the quantum mechanical model. And what we do with this is we show where electrons are going to be found around the nucleus of an atom. Sorry about that. So, like I said, we're going to use this information to show where electrons are likely to be found around the nucleus, which we refer to as an electron configuration. So, electron configuration shows the arrangement of electrons around the nucleus of an atom. So, we simply list out the location or the likely location of electrons in an element. We're going to have a list of different principal energy levels and sublevels in this PXN form. So the P is going to be a number. This is going to be our principal energy level. The X tells us what type of sublevel, what type of orbital we're in, whether it's the SPD or F sublevel. And then the N, that exponent, is going to tell us how many electrons are in that particular sublevel. So it's kind of like filling in like a checklist where you have to go in one place, you have to do one task before moving on to the next. But we're simply listing out everywhere that those electrons are going around the atom. So that P, that number that starts off with are energy levels. The energy levels are associated with like the row on the periodic table, how far away from the nucleus those electrons are going to be. The principal energy levels are divided into the sublevels, the SPD and F sublevel. And not every energy level has every type of sublevel. So for the energy level 1, the first energy level has one type of sublevel. So it only has an S sublevel. Whereas the second principal energy level will have two types of sublevels. So it'll have an S sublevel and a P sublevel. The third energy level will have three types of sublevels. So it will have an S, a P, and a D. And then the fourth will have an S, P, D, and F. So in general, the number of the principal energy level tells you the number of sublevels in that energy level. And they always go in order of S, P, D, F. So like the first energy level can only have an S. It cannot have a P, a D, or an F. These sublevels, so these sublevels are further split into individual orbitals. So the orbitals are those sublevel shapes that we looked at, but there might be more than one of them in a certain energy level. So an S sublevel, that sphere, only has one orbital. There's only one sphere or one lobe that electrons can go into. A P sublevel has three orbitals. So remember I said that kind of dumbbell or peanut shape can kind of rotate around the different axes. So there can be three different dumbbells or peanuts around that axis, where you can have one that's up and down, one side to side, and one going front to back. So a P sublevel has three different orbitals, three different places that electrons can go. A D sublevel is going to have 5 different orbitals, so 5 different places that electrons can go around an atom. And then that F sublevel we don't use very much can have 7 orbitals, so 7 different locations for electrons to go around orbital, or excuse me, around a nucleus. And each orbital can have up to 2 electrons. So these are the maximum number of electrons that can be in any given sublevel. So an S sublevel can only hold up to 2 electrons. A P sublevel can only hold up to 6 electrons total. A D sublevel can hold up to 10 electrons total. And an F sublevel can hold up to 14 electrons total. So these are important for when we are actually writing our electron configurations. These are the maximum numbers of electrons that are allowed in each sublevel type. The orbitals will come into play tomorrow when we look at orbital diagrams, which is just another way of writing out electron configurations. So let's get to actually writing electron configurations. This is where we are going to list out the locations of electrons around a nucleus. Some things to remember are that there are only 2 electrons per orbital. So those maximums that we just went over always apply. So we said S can have up to 2 electrons, P can have up to 6, D can have up to 10, F can have up to 14. And electrons are going to enter the lowest energy orbitals first. There is a certain order that these orbitals are filled in based off of their energy. So you have to know which order to fill these in. So you can write electron configurations using 2 different methods. The first one is using a diagonal diagram. This is probably the more popular way that we've had students write these in the past. It's pretty simple and straightforward to follow, but you have to be able to draw a diagonal in order to be able to use it. And then there's also a way that you can write electron configurations using the periodic table. This is a little harder to grasp initially, but it tends to be easier in the long run because you don't have to remember how to draw a diagonal. We're not going to tell you which method to use. I'll show you both methods, and then you decide which one you prefer over the other. So we're going to talk about drawing these using the diagonal diagram first. Before we can use the diagonal diagram, you have to be able to draw it in order to be able to use it. So I want to go through the steps of how to draw this out on your own. So if you're looking at the periodic table, the main part of the periodic table, not including the inner transition metals at the bottom, there are 7 rows of the periodic table. So we're going to list out our rows 1 through 7. Oops. And all of those are going to have an S sublevel that had the lowest energy. So all of these are S's. So that's the start. That's kind of going to be the long side of our diagonal diagram. We said that first energy level, that first row, only has 1 sublevel type. So that 1s is all that can have that principal energy level of 1. The second energy level, we said, has 2 sublevels. So it has a 2s, and then it also has a 2p. And all of these have a p. So we can list down the principal energy level with the p sublevel. And there is a 7p. We don't use it because it's those newly discovered elements, but it does exist. So that's the second column for our diagonal diagram. So our second principal energy level only had 2 types of sublevels. It had the 2s and 2p. So that third energy level is going to introduce our third sublevel type. So these are D. So it's 3D, 4D, 5D, and there is a 6D. There's not a 7D. We run out of elements. And then, like we said, our third energy level only has 3 sublevels, 3 orbital types. Then our fourth energy level has our F sublevels. So there's a 4F and a 5F. So this kind of looks like a sideways triangle if everything is lined up. So your diagonal diagram is going to be read from top to bottom, but from right to left diagonally. So our first diagonal is going to go through 1S. Excuse me. That's all that's on that diagonal. So then we have another diagonal that's parallel that goes through 2S. Our next one will go through 2P, 3S. Then it will go through 3P, 4S, 3D, 4P, 5S, 4D, 5P, 6S, 4F, 5D, 6P, 7S, 5F, 6D, 7P. So that gives you the order of those sublevels of those orbitals according to lowest energy. So this tells us the order that these need to be filled in order to put electrons around this nucleus. So like I said, you need to be able to draw this from scratch in order to be able to use it. All right, so here is that diagonal. So you can see we drew it from scratch, but this tells us the order that we go in to write an electron configuration. So some key tips that we're going to look at when writing these out is we want to always start with 1S. So we always start at the top of our diagonal and work our way down. And they always go in this order. So it always goes 1S, then 2S, then 2P, 3S, 3P, 4S, and then 3D. So there are some that seem out of order, but it's based off of the energy that they have. We need to make sure that we know how many electrons are in a stable atom of whatever element we're writing an electron configuration for. So remember, the atomic number is our number of electrons for that atom. You need to look at that previous slide to make sure you know how many total electrons can be in a different sublevel. So remember, S can only have up to 2 electrons, P can have up to 6, D can have up to 10, and F can have up to 14. And kind of using all of this information, you're going to write out an electron configuration. So we're going to go through some examples of these together. This is one of the things that you have to practice writing out. I will tell you, if you Google these, Google a lot of times has these out of order. So they're not necessarily in the lowest energy order, which is the proper way to write it. So let's look at some examples together. So first one we're going to do is sodium. And I'm going to show you how to use the diagonal as we go through writing this out. So sodium, if you look on the periodic table, is number 11 on the periodic table. That means that we have 11 electrons that we need to fill in around the nucleus. And I'm just going to write. I just like to write the number of electrons to kind of help me keep track of them overall. So we said you always go diagonal by diagonal and fill this in. So we always go through 1S first. So we have a 1S sublevel. And that sublevel, we said, could hold up to 2 electrons. We have 11 total that need a place to go, so we can put 2 in here. You want to fill each level before going on to the next one. So notice this is in that PXN format, and that means that we put 2 electrons out of our 11 around the nucleus. So we have to keep going. After 1s, go the next diagonal is going to be 2s. We said s can hold 2 electrons. So now we have 7 that need a place to go. That finishes out that diagonal. So go on to the next one. So after 2s, we can go to 2p sublevel. We said a p sublevel can hold up to 6 electrons. That leaves us with 1 that needs a place to go. So after 2p, keep going on that diagonal, we get to 3s. Now 3s, we said can hold up to 2, but we only have 1 electron left. Once you run out of electrons, you're done. So there's only 1 electron in this 3s sublevel. So this just lists out all the locations that we are likely to find electrons around this nucleus of sodium. So in sodium, there should be 2 electrons in a 1s sublevel, 2 electrons in a 2s sublevel, 6 electrons in a 2p sublevel, and 1 electron floating around in a 3s sublevel. So it's just giving us the locations of those different electrons as we go. Let's look at the next example. We have manganese. I want you to be careful. There is a manganese and a magnesium. Make sure you're looking at the right element. Manganese on our periodic table is number 25. So here it's a little bit bigger. We have 25 electrons that need a place to go. Sorry about that. So we still have to go in the same order. So we are going to fill in the 1s sublevel first. We said 1s can hold 2 electrons. So now we have 23 left. Keep going. That finishes out that diagonal. Go to the next one. We have a 2s sublevel that can hold 2 electrons. So we have 21 left. That finishes out that diagonal. So go to the next one. We have a 2p sublevel. We said p sublevels can hold 6 electrons. So we have 15 left that need a place to go. Keep going. The next one is 3s, which we said can hold 2 electrons. So we have 13 left. Keep going. That finishes out that diagonal. So go to the next one. We then go to 3p, which can hold up to 6 electrons. So we have 7 left. Then next is 4s, which can hold 2 electrons. So we have 5 left. And then after 4s comes 3d. And D we said can hold up to 10, but we only have 5. So 5 are going to go here to finish out this electron configuration. So you'll notice that this gets to be very repetitive for different parts, especially those beginning elements that you're using over and over again. All right, so I want you to pause the video and try bromine on your own. Bromine is number 35 on the periodic table. So pause it, try this on your own, and I'll go ahead and go through to write out the answer for you to check when finished. So bromine is going to go through 1s with 2 electrons, 2s, 2, 2p6, 3s2, 3p6, 4s2, 3d10, And that got us to 30 electrons. We have 5 left. After 3D is 4p, which will hold those last 5 electrons. So if you notice, all of our exponents should add up to equal 35. And this is something that is different from one element to the next. I'm going to go ahead and stop the video here before it times out, and there will be a part 2 to pick up with using the periodic table way. It will also have some exceptions for honors and looking at what do we do if we have an ion.